In this problem, we are asked to derive the compatibility equation for plane elasticity problems in terms of stresses. So we're going to be working in 2 dimensions because we have sigma x and sigma y. So what we can do is we can start out by setting up Hooke's law for 2 dimensions. So we're going to have our input stresses, sigma x, sigma y, and tau xy, and then we'll multiply by the essentially inner matrix, relating the Poisson ratio, relating Young's modulus, and the shear modulus to essentially get out the corresponding strains, our epsilon x, epsilon y, and the gamma xy. So what we can do is we can use matrix multiplication to multiply out to essentially get our strains. So let's do that. So essentially epsilon x will be equal to sigma x divided by E minus nu divided by E times sigma y. And then epsilon y is going to be equal to negative nu divided by Young's modulus, or E, times sigma x plus 1 divided by E times sigma y. And then last but not least, gamma xy is going to be equal to 1 divided by the shear modulus, which is G, times tau of xy. So now, one compatibility equation that we can write out for shears is that the double derivative of exx with respect to y plus the double derivative of eyy with respect to xx is equal to the double derivative of gamma xy with respect to xy. And now let me write this out. Let's use red here. So essentially what this is this notation is essentially short for the double partial derivative of epsilon xx with respect to y squared. So essentially these two are equal. And then we'll add the double partial derivative of epsilon yy with respect to x squared. And then same thing, so we'll have the double partial derivative of gamma xy with respect to x and y. And then so these are equal, these are equal. So it's just a shorthand, just so you don't have to clutter up your page and then have to write a whole bunch of Jacobi deltas all over the place. So that'll save us a little bit of time. But anyways, what we can do is we can then take our values from up here that came out of Hooke's law, and we can essentially plug them into this equation here. So by doing that, we can pull out the 1 over Young's modulus. We can get sigma xx minus nu times sigma yy, and then we'll have to take the double derivative with respect to y, and we'll have plus 1 over e times negative nu sigma xx plus sigma yy, and we'll take the double derivative with respect to x, and that'll be equal to 1 divided by g times tau xy with the double derivative, wait for it, with respect to xy. So now what we can do is we can write 1 over e, we have sigma xx, yy, so we're essentially just expanding out these derivatives, and now we don't know what our sigmas are going to be, we don't know what our taus are going to be, so right now we're just going to leave everything in its full derivative form without any cancellations, because we're not sure if they're constants, we're not sure if they're, let's say, just to the power of 1, because then if you have something to the power 1, take the double derivative with respect to that variable, then it should be 0. So we don't have any idea of what that information will be. So pretty much right now we're just expanding out these derivatives such that we have essentially nu and then sigma xx, double derivative with xx, so we'll just do comma xx. And we're just following that through. So it's definitely a lot cleaner notation, especially shorthand to do. And then what we can also do is we can expand g into its actual form. where G, the shear modulus, is equal to Young's modulus divided by 2 times 1 plus the Poisson ratio. So we can essentially write that out, and then we can cancel our Young modulus. And then we'll have tau xy, xy. And we'll leave that one just for a moment. And the reason we'll do that is because we can write out some compatibility relations such that sigma xx with respect to x plus tau xy with respect to y should be equal to 0. And then we also know that tau xy with respect to x plus sigma yy with respect to y should also be equal to 0. So what we can do is we can take the partial derivative of that first line with respect to x, and then with the second line we can take the partial derivative with respect to y, such that we get sigma xx with respect to essentially x squared plus tau xy with respect to yx is equal to 0. And then on the second line, after taking the or essentially the partial derivative with respect to y, we get tau xy is equal to, or tau xy with respect to xy, plus sigma yy with respect to yy, which is equal to 0. And then what we can do is we can essentially add these up to get that tau xy is equal to negative 1/2 of sigma xx with respect to xx plus sigma yy with respect to yy. And the reason we can write this is because tau xy with respect to xy is equal to tau xy with respect to yx. If I write this out in the derivative form, so we take the double partial derivative of tau xy with respect to dx dy, that is going to be equal to the partial derivative of tau xy of dy dx. So that makes things a little bit handier. So now we have something to replace our tau xy with. So now we can write this out such that we have, let's look at it before, so we'll have our sigma xx yy minus nu sigma yy yy, and just keep writing stuff out. So there's nothing new yet. And then now what we have is we will replace this equation for tau xy, and then what we'll do is the 2's will cancel, and then we'll multiply out the 1 plus nu, and then we'll also have that factor of minus. So that'll leave us with minus sigma yy minus nu sigma xx minus nu sigma yy, and then we'll also have a minus sigma xx comma xx. So essentially what we can do is we can actually cancel these two variables. So that'll help us clean up the equation a little bit more. So that'll leave us with essentially these. I'll write these out real quick. Okay, so now what I'm going to do is I'm going to write this in our partial derivative form, just so we can see a little more clearly what is essentially happening. Because we want to try to write this with respect to the gradient squared from above. And this will be with respect to x squared, and then we'll have our partial squared of sigma xx with respect to x squared, and then we'll add our partial squared of sigma yy with respect to y squared, and that'll all be equal to 0. Now what we can do is we can actually factor out partial squared over partial x squared plus partial squared over partial y squared. And then from this, we're left with sigma xx plus sigma yy, and that's going to be equal to 0. Now notice here, this term is equal to the gradient squared. So we are pretty much done, because now we can write that the gradient squared of sigma xx plus sigma yy is equal to 0. And we just proved it.